ሰላም ሰላም የፍሬንድሊ አካዳሚ ቤተሰቦች፣ ዛሬ ደግሞ የግሬድ 11 ፊዚክስ እናያለን። ከዚህም የኤሌክትሪክ ፊልድ ስትሬንግዝን አባት ፖይንት ቻርጅስ የምናየው ይሆናል። So the question says, what is the net electric field strength at point P, this point in the system shown below, due to these two charges? So we are solving this problem. We are discussing the main concept why we use certain approaches while solving this problem throughout the problems. Now, we are asking to find the electric field. So the electric field strength, since it is a vector quantity, we use that is a force per unit charge, a unit point charge that brought to the near to another charge that it feels certain either pushing or pulling effect. So the electric field is a region about this charge. If this another charge, certain point charges are brought near to this charge, it will feel certain electrostatic force. So which is equal to the charge times the K constant, Coulomb's constant, times the radius square. So the electric field due to this charge, let's say this is Q1, this is Q2, and this one is charge. So the electric field 1 is given by the charge that due to the charge 1, so Q1 times K divided by R1 square. Now look, what is the distance from this point up to this charge, which is 2 meters plus 1 meter. So the distance R1 is the distance that this point has from charge Q1, so which is 3 meters. And the charge is 1 microcoulomb, so it is 1 times 10 to the power of 6 coulomb times 9 times 10 to the power of 9 nanometer square per coulomb square divided by the radius square, the distance between the charge up to a point. Because we know that electric field is a region, a point about around this charge, where another charge if counts may feel certain repulsion or attraction force due to this charge, which is 3 squared, 3 meter squared. Which is how much? 1 times 9 times 10 to the power of minus 6 plus 9 meters square. Now look, Coulomb squaring and this one will be 9 meters square. So divided by Newton meter square per Coulomb divided by 3 square. 3 meter square is 9 meter square. So meter square by meter square, 9 by 9, which is 1 times 10 to the power of 3 Newton per Coulomb. 1000 Newton per Coulomb. Force field will be experienced due to this charge. So the point charge, this point charge will experience, if the certain test charge comes to this point, it will experience this much electric field due to this charge Q1. Now let's find for Q2. So the electric field due to Q2. Now look at R2, which is the distance between this charge Q2 up to this point, which is equal to how much? This is 1 meter. So electric field E2 is equal to how much? Q2 K over R2 squared. Q2 is how much? Minus 3. But we don't care about the sign. We'll use it later on to determine the direction of electric field. But for time being, it's not needed because it is not scalar, vector quantity, it's scalar, and it only shows which more charges it will have. Is that positive or negative? So this has excess of electron, indicate that's negative. It means it lost, it gained electron matter, which is 3 times 10 to the power of minus 6 coulomb times 9 times 10 to the power of 9 Newton meter square per Coulomb square divided by, again, the distance between them is 1 meter, 1 meter square is 1 meter square. Now meter square cancel out by meter square, Coulomb will cancel out, and which is equal to 3 times 9, which is 27, and in the power of minus 6 plus 9 is 3 Newton per. You see, the nearest the charge is, or the point is to the charge, the higher the electric field. The electric field will be very great. Again, as the charge, magnitude of charge increase, the electric field will be greater. Whether it is repulsive electric field or attractive electric field. Now we have got the electric field due to charge 2 and charge 1. But now, since electric field is vector quantity, we have to determine its vectors. Now look, if the electric field is, the charge is positive, as you remember, as we discussed last time, so we have discussed, or you may know. So now let's close the redraw. This is -1 minus Q. So this is Q2. This is Q1 from this one. Then let's have our point. This is the direction. Straight line. It's fast for this one. This one. This is 3 meter. 3 meter. This is 1 meter. Just we have this one. Yeah. That's it. Okay. So this is 2 meter. Now, from this one, we have got, if charge is negative charge, electric field is towards that charge every time. So the electric field lines always runs from toward negative charge and outward from positive charge. You know this one from the concept. So the electric field due to this charge is to every direction, it is outside of this charge. And it's also this direction. What is going on about now? What is it now? It's out of the charge. So the electric field E to 1 is equal to toward X direction. That means the electric field due to Q2 is which direction? That direction, which is equal to how much? Which is 1 times 1000 Newton per Coulomb. This is that direction. Why? Because the positive charge, electric field positive from positive charge, points out from a charge to the point, when a point to a point matter. But the electric field due to this negative charge, since the electric field due to negative charge, since the point charge negative ከሆነች ወደ ራሷ point ስለሚያደርግ it comes to inwards the charge, so it is this direction, which is how much? E1 is how much? And E2 is how much? 27 times 10 to the power of 3 Newton per Coulomb. So that's it. Now look, we will use the vector direction. In net electric field is the component ካላቸው this already x-axis ናቸው ተቃራኒ. This will go there to that way and this goes this way. And the net electric field is the sum of E1 plus which is the sum of the vector sum of the two, since it's vector quantity. So 1000 Newton per Coulomb. Minus, because this is in the negative direction, so plus of minus 287,000 Newton per. That's it. So the net units, we have the direction, negative direction. So negative 27,000 minus 1,000, negative plus 1,000, which is negative 26,000. Write it as minus 2.6 times 10 to the power of 4, which is approximately near to 1 Gauss, 2.6 Gauss. That's it.